Hello guys, welcome back. Here we're doing 2003 AP Calc BC free response Form B. Form B is always a little bit harder than usually the Form A, so the questions here are a little bit difficult. I'm going to do number 2 right here. It says the figure above shows the graph of the circle, and he gave the equation of the circles. And he told you an intersection, which is really nice, and then asking us to set up an expression involving one or more integral with respect to x, represent the area of R. We know that the area of R it's right over here where these two intersect. But realize if we just do a normal integral like this, if you have a function and trying to find like the integral, you have an upper bound. But in this case, the upper bound is separate. You have a section over here, you have a section over here, which meant if you're doing by dx, which is with what it's asking for, we need to separate it right over here. From this side of the left, it's the smaller circle, and from the right, it's going to be the bigger circle. So let's get started. Now we have to rewrite this in terms of x, so it's y squared equals 2 minus x squared. So y is square root of 2 minus x squared. Same as this one, so x minus 1 squared equals 1. X minus 1 equals square root of 1 minus y squared. So x equals to, oh, oops, see how I did a mistake. You're supposed to write this in terms of y, so you're supposed to do it by y. So y equals square root of x of 1 minus x minus 1 to the square. Whoops, here's 2 minus x to the square. So let's do the left part first. You have integral of 0 to 1. So the left part is small circle, which we can tell is this is the small one, and its radius is 1. It's this one over here. So it's square root of integral of 0 to 1 of square root of 1 minus x minus 1 to the square dx. But we're not finished yet. There's a second part, and the second part is plus integral. So if somebody wondering what this point is, it tells you that x squared plus y squared equals square root of 2, which means the radius of this circle is square root of 2. So it's x squared plus y squared equals 2. So this point here is square root of 2, 0, right here. So it's going to be from 1 to square root of 2. And this is a big circle, which will use this one, so it's the square root of 2 minus x squared dx. Since it doesn't ask us to evaluate it, we can just leave it right here. Now let's do B. B is asking us to set up an expression involving one or more integral with respect to y that represent the area of R. And let me erase this first. If you really want to look at the return with respect to y, you can literally just turn this whole graph 90 degrees counterclockwise, and you can see that in this case you are much easier because you have an upper bound of the bigger circle and the lower bound of the smaller circle. You can just use integral of if the higher bound minus the lower bound. Then the problem is just rewrite this in terms of y. So for the big circle, x squared plus y squared equals 2, which meant that x equals square root of 2 minus y squared. As well as this one, you have x minus 1 to the square plus y squared equals 1. X minus 1 equals square root of 1 minus y squared, which meant x equals square root of 1 minus y squared plus 1. So we can set up our integral as integral. Remember, in this time is in terms of respect to y. So what's our limit of integration? It tells us that it intersects at this point, which gives us a y value of 1. So we limit integration 0 to 1. The higher bound, which is the bigger circle, square root of 2 minus y squared. And the lower bound, which is smaller circle, minus square root of 1 minus y squared plus 1, and this is dy. Now he's asking us for C, which uses polar equation of the circles. He gives us the polar equation, and respectfully is asking to set up an expression involving one or more integral with respect to the polar angle. This is very interesting because, again, like part A, we can't do this just by a simple integration, because over at the intersection you have this area right here that this was bounded by the big circle, but this part was bounded by the smaller circle. So again, like part 1, we'll have to integrate them differently. Remember how to integrate a polar angle is 1/2 the integral of r squared with d theta. So using this equation, we can integrate the big part, the part that was the arc of the big circle. And this is easy because it's just going to be integral of 0 to pi over 4 square root to the square d theta, and it's 1/2. Why is it pi over 4? Because at this point they have the same r value, which meant square root of 2 equals 2 cosine theta, and you solve for theta, you have theta equals 4 pi over 4. So at this point, the theta angle is pi over 4. It doesn't really matter in this case because it doesn't matter in this case because you're going to need that in the second part of integration too. Since we already have this part of the graph, we want to find this small part of the graph. And let's go again. 1/2. We know it's going to be the integral of r cosine 2 cosine theta to the square d theta. But what is the limit of integration? Let's see. It starts right here where the theta angle is the same as the ending point. So as the ending point of the first one. So the starting point will be pi over 4. But what about the ending point? As the ending point, see how this approached 0, so which meant that 2 cosine theta, which this meant 2 cosine theta is 0. You may solve this and you find out that pi equal to is 0, theta equals to 0, but that's not what we're looking for because that will be the starting point, which meant also that we're looking for, that meant we're not really looking for when r equals 0. We are on the other side trying to figure out what the theta is. Well, it's at this point over here. And since you know we start at 0 and it's not going a quarter of the way through, we know that in this case theta is pi over 2. Now we have our upper bound of limit of integration as pi over 2. Make this a little bit cleaner. There's your answer for part C. Can you simplify this? Yes, you may take out the 1/2 and combine them, but that won't be necessary in AP exam because it's asking just for integration, not to simplify. And remember, don't waste time doing that, and really be glad that they didn't really ask us to evaluate this in calculator. Otherwise, it's to be a pain. All right. Again, thanks for watching.